quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Welcome to Atomic Theory Part 4. We're starting off the fourth of, I guess it'll be 5 overall sections on atomic theory and some of the people that helped contribute to atomic theory through the years. Today we're looking at what's called the Rutherford Bohr model and how we got to that model with the contributions of a scientist named Niels Bohr. And before we talk about him, I'll mention one other person to you. Today's episode, however, is brought to you by Libby's Plum Pudding. In all seriousness, this is actually an article, or I guess it's an ad that I found online from a 1903 magazine, I think, or a newspaper, that advertising a particular brand of plum pudding. And so I found a little bit more information about what they look like, and this is a legitimate ad from 1903, which is actually, gosh, right around the time that Rutherford was doing the work of the gold foil experiment, and that Thomson derived the plum pudding model right there around 1900. So kind of a fitting advertisement that someone's sharing with the world, and kind of gives us a little bit of idea of, if nothing else, how far advertising has come through the years. So the two people I'm going to mention to you today, and we're going to keep this one pretty short. The first, really quickly, is a fellow by the name of Max Planck. Planck, right around 1900, again around the time of that advertisement for plum pudding. He was a German physicist, and among the many things that he did was he found and established a connection between the temperature of an object and the color of light that it gives off. You've probably all seen pictures of glowing hot metal, and usually it's glowing some color. Often it's just glowing orange. We can quite easily do that in the lab. Take a piece of thin metal, a wire loop or something, and heat it in the Bunsen burner for just a few seconds. It'll start to glow. Or if you do any branding with someone who does ranching for a living, you've seen glowing hot brands that then of course leave their mark in a very dramatic way on the cattle that are being branded. Well, metal glows a particular color as it's related to the temperature of the metal itself. So the color and the temperature are connected, and Planck found a way to establish the connection more formally between those two things. He also originated for us what's called quantum theory. You can hear more about quantum theory with our next person. Well, it's 2 people down the road from now, but the next video will be the 5th and final part of atomic theory. We'll talk a lot more about quantum theory in there. Quantum theory has to do with energy, which is the small unit of energy that's sort of like the atom equivalent. The smallest unit of energy we call a quantum, or plural we call it quanta. And so quantum theory is more or less a type of energy theory that has to do with electrons or atoms. We'll talk more about that next video. The person who's the more important player of this video today is a guy by the name of Niels Bohr. As I mentioned, he's a Danish physicist, so he's from Denmark, and he studied also with Thomson and was a colleague of Ernest Rutherford, so he worked around the same time. Rutherford and Bohr are closely linked, not only in history as far as their contributions go, but also being, of course, from the same time frame, and having been very ardent collaborators with each other. They were often to be sharing their discoveries, their conclusions, sort of building on things with each other collegially in that way, which isn't always the case in science. It's often very competitive. These two guys seem, from all that you'll read about them, to be very good together as far as helping each other build and build and build on the atomic theory, which is obviously to our benefit. So it's kind of nice that we've got one thing called the Rutherford Bohr model of the atom. What Bohr sort of starts his work on then is wondering, as it's related to Planck and those colors, is why certain metals would only glow specific colors when heated. Hotter and hotter temperatures, different colors would be emitted, but not other colors. So when you heat a piece of metal, it may glow orange like you see in this picture here. Or you might see it glowing after that's been heated for a while hotter. You might see it at a higher temperature glowing blue. Well, why doesn't that same piece of metal, say, glow an obvious red, or perhaps a green or a purple? Why do we only get these specific colors and not others? And Bohr looked at that observation, and I'm thinking about the scientific method again, the observation, and it realized that the Rutherford model of the atom, and certainly not the plum pudding model, none of those could explain why atoms would give off certain colors and not other colors. He figured it had to do something with the structure of the atom, and he believed specifically the electrons in that cloud that Rutherford drew in his model were not quite what Rutherford thought. At least that wasn't nearly enough detail to explain why this would happen. So he had to come up with, develop a hypothesis to help us understand why. What he does to explain that then is what's explained here. First, he theorized, or we might say hypothesized, that electrons were found at distinct distances from the nucleus of the atom and not in a random cloud. So think about this ladder as you see here perched against the wall as being sort of a way of explaining or showing, showing the electrons' positions as they relate to the nucleus. So in this particular example then, or the ladder analogy, the nucleus would be down here at the ground, and then each successive rung up the ladder would represent a distance or an energy level in which the electrons could be found. And as you go further and further from the nucleus, which again would be down here in the grass, you would go higher and higher and higher in energy, further and further from the nucleus. Notice this is an odd ladder in that the spaces of the rungs are not consistent as you would want in a normal everyday ladder for safety's sake. This is a little bit more like the representation of what Bohr imagined the energy levels to be. Not evenly spaced like a normal ladder, but actually getting successively closer as we go up the ladder higher and higher. They get a little bit closer together. That's not an important detail for today, but it is there. So those rungs were called energy levels, or he calls them energy levels. And so will the next person in atomic theory, which will come in the next video. So this idea that the electrons were not in a cloud, but in very distinct distances, or what we would call, sort of for simplicity, we would call them rings. Again, the better word is energy levels. So electrons were found not in a cloud, but in specific rings. Now this is probably what a lot of you drew in that first picture that I asked you to draw in your notes way back before we started. A central nucleus with many rings around it in some way. That's a lot of people's typical first impression of an atom, and not a bad one actually. That's accurate enough for most things that we do. And we call that the Rutherford Bohr model. So what you see here in the picture is actually a smaller version of the Rutherford Bohr atom model. In this example, you see there's only a nucleus with the plus charge in the middle. So we've got that right in the center of that circle. And then around it are two other rings in which the electrons would be found. So this particular ladder would only have two rungs, the first and second energy levels. The idea that Bohr then used to explain why the colors were being given off is that as electrons gained energy, they could jump from a lower level, which we call the ground state, to a higher level, which is called an excited state. Now the ground state is the lowest level where you normally find that electron, and anything above that would be considered an excited state. So it could jump up one energy level or one ring or one rung in that ladder, or it could jump two or three or more energy levels higher. The more energy it absorbed, the higher it might jump. The excited state, Bohr hypothesized, is very unstable, and so the electron doesn't tend to stay there very long. The electron will fall immediately back down, basically in an instant, and as it does, it will give off the same amount of energy that it took in. And sometimes that energy is released as a visible wavelength of light. And this is why we can see color from a heated piece of metal. At least this was Bohr's hypothesis. As you heat that metal, the electrons gain energy from the heat, and that makes them jump from a ground state up to an excited state. And then as they fall, they give that energy back to you, the same amount of energy, in a different form. So energy is conserved, but it comes back in a different form. It's a bit like, I think about it a bit like if I gave you $1 and you gave me 4 quarters back, you would have given me the same amount of money back, but it has a very different form. It has very different properties. You can't jingle a dollar bill in your pocket, but you can jingle 4 quarters. You can't fold 4 quarters, but you can fold a dollar bill. And so there's these different properties about the same amount of money. Well, in this case, heat energy goes in, light energy comes out in this example. We can do the same thing, it turns out, with electricity. Pump electrical energy in there or electricity in there, and it actually can do some of the same sorts of things. It's a little bit simplistic to say that, but the idea being that energy can be exchanged or changed forms, from a lower energy ground state to a higher energy excited state. And so as it falls, it gives that energy back as light. Why each color was unique, why do different metals give off different colors, that's an important explanation then. So Bohr's idea was that the energy levels are not evenly spaced in any atom, and in each element they are uniquely spaced. So again, looking at this ladder, not only is each energy level spaced differently, not evenly, like a normal ladder would be, but if I compare the spacings in, say, copper to the spacings in calcium, or the spacings that you might find in lithium or strontium or sodium or potassium, you'll find that the spacings are different in each element. And that has to do with a number of things, one of which is the strength of the protons in the nucleus and how many of those there are, and other things that we'll talk about more as the semester goes on. So every element then, as it says here in the second bullet, has different distances between levels, and the falling electrons, as they fall from an excited to ground state, can only fall those specific particular distances. So each element then has its own set of colors that can be given off that kind of correspond to those rungs on the ladder. We call that set of colors the emission spectrum, and you see that term here. An emission spectrum. The spectrum is more or less just all the colors of the rainbow, we might say. An emission spectrum for an element is the specific set of colors that that element can give off when heated. Or when excited, when its electrons are excited. And the colors in between are skipped. What I'll show you here on the last picture of the day is a set of a few spectra. The plural for spectrum is spectra, so these would be 4 emission spectra. You can see maybe along the edge of the screen, it's quite small here, that the top one is for hydrogen, then for helium, mercury, and uranium as we go down. And you notice a couple of things. One, each of those is very specific. They remind me all the time of like a barcode. Or if you've seen those bands of DNA in an electrophoresis lab in your biology class, it might remind you of those unique band patterns that you get from different people's DNA. Or if you've seen one of these sort of mock crime shows where they're showing the DNA patterns of the unique criminal signature. Well, these bands are unique to each element as well, and you could think about it like the DNA or the barcode of the element. Very unique. There's nothing about any two elements emission spectra that would be the same. There could be similarities, but they're not exactly the same. And we've been very precise in our labeling of what the frequencies, or in this case you would say the wavelengths of light would be. So notice here in the hydrogen row, the very top row, there are basically 4 colors showing up: a red, a light blue, and a purple, or 2 over here. The helium bands, there's a red, but it's a different red than before, a yellow, 2 or 3 more blues, all of them different than the one in hydrogen's row, and then 2 purples, and again each of those are different. And the same thing for mercury. There's 1, 2, 3, 4, 5, 6, 7, 8 different stripes here for mercury. And then down at the bottom, uranium, which has 92 protons and 92 electrons, has, gosh, more bands than we can count. And so each of those is different. Now, what color would you actually see if you saw hydrogen being heated? Well, I'll show you some examples of that in class, and you'll find out that it's really not red or blue or purple. It's actually the combination of those. And the same thing's true for helium and the other elements too. What color we see with our eye and what color we see if we're able to separate those colors out, which we will do in class, is very different. And so it's a matter of sort of splitting off the colors, separating them off, like you would do if you shined a light through, say, a prism, a piece of glass prism, and saw the rainbow coming out the other side, or if the sunlight shines through the raindrops in the sky and makes a rainbow, you see all the colors of the sun's light, which essentially is every color of our rainbow, right? Imagine, if you will, that the sun is shining through a cloud and you saw a rainbow, but it only had certain colors in the stripes and others were missing. That would be totally bizarre. It'd be really cool, actually, but it'd be quite bizarre. It'd be a little freaky. Like the green band is missing. That'd be really strange. That's kind of what these look like. It's a rainbow that only has certain parts showing up. So that's kind of the idea as far as the colors that go with Bohr's hypothesis. And it turned out that he was very accurate with it. He did a lot more work than what I'm sharing with you here. He did a lot of calculations that helped explain very specifically and predicted very, very precisely the colors of hydrogen's emission spectrum. So the colors that you're seeing on the top bands here on the hydrogen screen were colors that Bohr would have stared at and studied and calculated like crazy through years and years of work. His work wasn't good for every element, but it was great for hydrogen. And because of that, he was a huge stepping stone toward a much better understanding of the atom and of our atomic theory of today. So the next thing up will be to look at these colors with some funky glasses in class. And then the other thing will be to do Lab 10, which is the flame test lab. And that'll be coming up here in the very near future. So until then, I hope you get the notes down, and we'll talk to you later.
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave.
Welcome to Atomic Theory Part 4. We're starting off the fourth of, I guess it'll be 5 overall sections on atomic theory and some of the people that helped contribute to atomic theory through the years. Today we're looking at what's called the Rutherford Bohr model and how we got to that model with the contributions of...
A laser shines a coherent beam of light through a film disc containing 2 parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, QuantumLaserPointers.com.
A scientist named Niels Bohr. And before we talk about him, I'll mention one other person to you. Today's episode, however, is brought to you by Libby's Plum Pudding. In all seriousness, this is actually an article, or I guess it's an ad that I found online from a 1903 magazine, I think, or a newspaper, that advertising a particular brand of plum pudding. And so I found a little bit more information about what they look like, and this is a legitimate ad from 1903, which is actually, gosh, right around the time that Rutherford was doing the work of the gold foil experiment, and that Thomson derived the plum pudding model right there around 1900. So kind of a fitting advertisement that someone's sharing with the world, and kind of gives us a little bit of idea of, if nothing else, how far advertising has come through the years. So